We are told that recycling is a simple act of civic virtue, a clean, easy habit performed in the comfort of our own homes.
We sort plastic from paper, glass from metal, and deposit them into designated bins. The participation rates are often lauded as successes, suggesting we have found a sustainable answer to the waste crisis.
Yet this idealized image belies a far more complex reality. What happens after the curb? Your sorted materials don't simply vanish into thin air. They enter an industrial gauntlet.
These massive material recovery facilities, or MRFs, are not magical processing centers.
They are highly technical, often chaotic ecosystems of machinery and human labor designed to sort commodities based on market demand, purity standards, and technological capability.
The initial sorting challenge is immense, separating thousands of different materials that have been mixed together by consumers over decades.
The first gauntlet they encounter is the sheer scale of industrial separation. At a modern material recovery facility, or MRF, the process begins with massive conveyor belts and an overwhelming series of mechanical filters.
This isn't just about picking out aluminum. It's a complex act of material science.
Powerful magnets pull ferrous metals from the stream, while air classifiers lift lighter materials like film plastics away from heavier containers.
The most sophisticated step involves optical sorters machines that use near-infrared light to identify and separate polymers by their chemical signature, such as distinguishing PET from HDPE, regardless of whether they are blue or clear.
This initial sorting stage is a marvel of engineering complexity, transforming mixed waste into discrete streams of marketable raw materials. This initial sorting is labor-intensive, requiring skilled workers to refine the output streams.
Manual pickers finalize the fun?
The process doesn't end at the facility gate. What happens next is dictated by global commodity markets, a complex web of economics that determines which materials are valuable and which remain mere waste.
The price of oil, for instance, has historically influenced the perceived value of plastics, sometimes making virgin plastic cheaper than recycled alternatives.
This fluctuation means recycling streams are not guaranteed commodities. They are highly volatile market goods.
Industry experts confirm this reality. The demand for sorted bales changes constantly, requiring facilities to adapt rapidly or face economic challenges.
The viability of an entire recycling stream often hinges on unpredictable external factors and global industrial demand. Consider aluminum versus mixed plastics. One commands stable global prices while the other faces unpredictable demand shifts.
This economic reality forces innovation, pushing facilities to seek higher value streams and minimize contamination for market acceptance.
The complexity deepens when we examine plastic. These materials are not a single substance, but thousands of distinct polymers, long chains of molecules that dictate how they must be processed.
A bottle made from PET requires vastly different chemistry than one made from HDPE. This material specificity is the first major hurdle for recycling infrastructure.
When contamination occurs, even minor mixing can render entire batches unusable. Beyond simple sorting, we face the technical challenge of polymer degradation.
Mechanical recycling, the standard process, can only break down plastics to a usable level if they are chemically pure and consistently sorted.
To overcome this, advanced methods like chemical recycling or pyrolysis are being developed, aiming to return plastic back to its original molecular building blocks.
These technologies promise a circular economy, but their scalability and energy demands remain subjects of intense engineering study.
The challenge of purity necessitates movement. Once materials are sorted at local material recovery facilities, they rarely stay put.
They are compacted into massive bales, a commodity ready for the next leg of a complex logistics chain. This is where waste management transitions into global trade.
Bales of PET plastic or aluminum sheeting leave regional facilities and board specialized fleets. Semi-trucks heading to distant processing hubs, trains carrying loads across state lines, or container ships crossing oceans.
The journey itself requires immense coordination, linking local collection points to highly specialized processors, sometimes thousands of miles away, or even in different continents entirely.
This shift reflects a profound change. Waste is no longer just a local problem. It has become a global commodity whose value depends on its efficient transport and the market demand for its raw components.
But what happens when these materials finally arrive at their destination? The reality of recycling processing plants is often far more complex than the ideal depicted in public service campaigns.
Here, mixed streams of materials are sorted again,
sometimes multiple times, to extract specific polymers or metals. The goal is always recovery, but perfect circularity remains an aspiration, not a guarantee.
Much of what we call recycling actually involves downcycling, using a high-grade material for a lower-quality product.
For instance, PET bottles might be shredded and repurposed into park benches or industrial filler, losing some of their original structural integrity.
The output is diverse. Everything from new packaging components to construction aggregates that simply replace virgin materials in concrete mixes.
This process transforms waste streams into commodities, but it also introduces variability, meaning the end product's quality depends heavily on the...
But even with sophisticated sorting and reprocessing, contamination remains an unavoidable reality. Mixed plastics, soiled items, or complex composites often exceed the economic threshold for recycling.
These materials form what is known as the residual waste stream, the fraction that cannot be processed efficiently. Managing this residue requires distinct approaches.
Some facilities employ advanced thermal treatment, converting high-volume non-recyclable waste into energy and inert ash. Others rely on modern sanitary landfilling, designed to minimize environmental impact while accepting mixed residuals.
These endpoints represent critical points in the circular economy model. They are where material recovery goals meet practical engineering limits.
The true measure of a recycling system is not just its potential, but how effectively it manages this necessary remainder.
The choice between these methods, energy recovery versus controlled disposal, is dictated by local infrastructure and policy. Ultimately, managing this unavoidable remainder is...
The challenge of the residual stream points to a fundamental need for systemic overhaul. Future waste management cannot rely on incremental improvements. It demands paradigm shifts in technology, policy, and design.
Emerging solutions are tackling these limitations head-on. Advanced sorting facilities are integrating sophisticated AI and robotics, capable of identifying and separating materials far beyond current manual capacity.
Policy levers, such as mandatory deposit return schemes, ensure high-value containers re-enter the loop with minimal loss. Furthermore, the most profound change is happening upstream, material design itself.
By mandating design for circularity, manufacturers are rethinking products to use fewer virgin resources and make their components inherently recyclable.
These converging efforts, from advanced engineering to legislative mandates, are charting a course toward true resource independence. This holistic approach, combining smart infrastructure with legislative backing, is crucial. It moves us from simple waste disposal to a circular.
The journey of that single bottle or sheet of cardboard is not over when it leaves your home bin.
What we often see as the end point. The curb is merely the beginning of an incredibly complex global commodity chain.
This process involves sorting facilities, chemical processing plants, and international markets, transforming discarded materials back into feedstocks for new products.
It is a massive, intricate infrastructure loop that requires advanced technology, stable economies, and continuous policy support to function at scale. Yet we must be careful not to treat recycling as the sole answer.
True sustainability demands more than efficient disposal. It necessitates fundamental shifts in how we design, consume, and value resources from the outset.
Only by addressing the source, the initial material choice and product lifespan, can we truly close the loop and build a resilient economy for tomorrow.